My name is Takto. Today, I will introduce the paper targeted synthesis of ZSM5 nanoseed with controllable V-axis thickness and aspect rate, strategy and growth mechanism. Thank you very much for your attention. First, I told you some basic information. The title is mentioned, and the journal is Chemistry of Materials. It is published at 2022 years. And there also is there. As a keyword, I was laid advanced characterization for reaction mechanism, how to make nanoseed. Zeolite are porous materials with regular pores, and the zeolite presented here, ZSM5, has two intersected 10-member ring channels. Because of its characteristic, highly desired material for catalytic reaction and membrane separation. But there are problems. In bulk zeolite, the long micropores make it hard for molecules to diffuse efficiently. However, once the crystal size drops below 50 nanometers, this diffuse limitation becomes much less of an issue. To get around this, researchers have been working to make ZSM5 in special shapes like super thin nanoseed, so that molecule can access the active site more easily. The thinker, the nanoseeds are along one direction, called the B-axis, the better the diffuse and catalytic activity. The issue is it's not easy to control the size and thickness of these nanoseeds during synthesis. So this study aimed to come up with a clear strategy to make ZSM5 nanoseed with exactly the thickness and aspect rate they want. They also dig into growth mechanisms, basically figure out how they make nanoseed from it at the first place. The nanoseed was synthesized using the seed layer method. First, mixing the reagent at indicated rate, and stirred it for about 6 hours at 35 degrees. This gave us a clear solution for after hydrolysis. Next, we warmed up the mixture to 45 degrees to get rid of the ethanol that formed during tails hydrolysis. Once that was done, we translated the solution into a Teflon line autoclave. They heated it at 70 degrees without stirring for somewhere between 24 to 96 hours. The longer we let it sit, the more concentration the seed suspension began. In the end, we get seed particles that were about 20 nanometers in size. Next, nanoseed were synthesized, mixing these ligands at the indicated rate, and heated in Teflon autoclave at 170 degrees for 20 hours. After heating, let it crystallized. We collected the solid by centrifuging it a few times and washing it with deionized water until the pH was neutral. Then we will dried it overnight at 8 degrees. After that, we treated the sample in air at 540 degrees to burn off the organic and get the H-form ZSM5 nanoseed. These crystals were indicated by XRD. This is STEM image of the crystal we obtained. The weight percent shows the concentration of seed crystal using during the synthesis. As you can see, the nanoseed or the A-axis, B-axis of C-axis, all axes are getting thinner as the seed concentration increases. And then this paper discussed the reason why such nanoseed can be synthesized. First, the small seed crystal, about 20 nanometer in size, has a very clean and defined surface, which really helps speed up the easy stage of crystal growth. Basically, they make nucleation happen faster and kickstart the formation of MFI zeolite quickly. Among the surface, the 010 surface is most stable, energy-wide, and it's great at attractive certain additional because of how the silicon and oxygen atom are arranged here. So, what happened at ammonium fluoride tend to stick to this 010 surface? First, this is first step. Then the fluoride ion start reacting with the silicon atoms in zeolite frameworks, especially at their special cage like site called 456 cage. And that from a negative charge structure. This is second step. And this negative charge unit gets pulled towards the positive charge template molecules, TPA+, which then starts running among the AC plane of the crystal. This is third step. That makes sense because previous studies have shown that where the fluoride ion go tend to influence how the organic frame template molecular arrange themselves. Meanwhile, ammonium fluoride also helps to dissolve some of the silicon, making it easy to structure to grow, thanks to the TPA template guiding the process. The crystal grows mainly among the AC plane, and then that gives rise to thin nanoseeds that are aligned around B axis. And it is all happened very fast. This is fourth step. In summary, the use of seed grease and ammonium fluoride enables the creation ZSM5 nanoseed. If their crystal could be synthesized at thin films, higher performance as molecular sieve is expected. Thank you for listening.